We could also use integrations over one variable to find surface areas. And here I'll tell you that in Calc 3 you'll learn the more general formula for a surface area. And so that's the most appropriate setting to talk about surface areas. Okay? But you can find surface areas of very simple shapes using integrations over one variable. And, you know, this is mainly shapes that you get by revolving a curve around a particular axis. Okay, and so you could see over here, if we have this curve over here, okay, so take that to be a curve. Well, we can revolve that curve around the x-axis, and then we could talk about the surface area of that shape. Okay, the surface area of that volume or that shape that you'll get from revolving it around the x-axis. Okay, here is the formula, and to give you an intuition about that formula, okay, what you're doing here is, you'll recall this right here is the length of a curve. Okay, so this is the small ds. All right, that part there is the small ds. Okay, or you could think about it there as ds. It's the arc length. It's a small arc length of the curve. And what you'll do is rotate this around. Okay, and once you rotate that curve around, that ds multiplied by 2 pi f of x. What is that 2 pi f of x? It's basically the what you'll get if you rotate. It's the circumference that you will get from rotating a point on that curve. Okay, and so, you know, here we have, for example, if we'll take this point here, and if we're a little more careful, we could rotate around this way, and this is going to be it's going to have a radius of f of x. Okay, if this curve over here is f of x. Okay, and so you'll take that circumference and multiply it by little ds, and what does that give you? That gives you a small surface area for a small segment of the total shape. And that's how that formula works. We could also have rotated around y, okay, instead. And if we rotate around y, this is the formula again, this is the arc length, and this is the circumference that you would get from rotating a point on that curve about the y-axis instead. So let's take a look at a concrete example. So a spherical zone is produced when a sphere of radius a is sliced by 2 parallel lines. Okay, so you'll take a sphere and you'll slice it into 2 parallel lines. That result when the first plane is oriented vertically and cuts the sphere in half, while the second plane lies h units to the right, where 0, so h has to be greater than 0 but strictly less than a. We want to find the surface area of that shape. And so this is how that looks. Okay, this is how that shape looks. You could see the two planes. One is intersecting right at the middle there of the sphere, and the other one is h units to the right of it. Okay, and what we could do is rotate this shape. Okay, we'll rotate about the x-axis, and we want the surface area that we're seeing there as we rotate. Okay, we want the surface area that you would get between those two parallel planes. Okay, and how do we compute that? Well, we are going to do this integral. So let's take a look. Here we have f of x, that's the curve, is equal to the positive hemisphere of the circle. And we have to take the derivative because that's what the formula wants us to do. And so we'll use the formula. We plug in our results into the formula, and we get this expression right here. And notice that we're integrating from 0 to h because we just want the surface area from 0 to h, okay, not the remaining part. And we end up with, after doing this integration, we end up with this expression, 2 pi ah. Notice that if you take h to equal a, you'll get 2 pi a squared, which is indeed half of the surface area of a sphere. Surface area of a sphere is 4 pi a squared, and so if you take h to equal a, you do get half the surface area of a sphere. So that agrees with what we do know about the surface area of a sphere.